Okay. Don't think anyone else is coming, so we'll just get started. Last thing we talked about, to remind you, is square roots. Square roots were the topic that we last talked about. The last proof I did, I'm not going to redo the proof, just remind you of the proof. The last proof I did was proving that the square root of x squared is just the absolute value of x. Bring in a little bit of bells. Here's the two example problems that we did to help trigger your mind a little bit. So the absolute value, the square root of negative 5 squared is equal to negative 5, which happens to also be 5, right? It's the same thing as the absolute value of negative 5, which is 5. So you're correct, the answer is 5, but I want you to see that it's negative 5, which is the same thing as 5.
Okay.
Good? All right. What's this one? 13, right? 14? 13?
How much is 160?
160?
69 is 13. It looks like it's 189 to me.
189, you fell for the trap again. The square root of 189 squared, the square and the square root onto each other, is just 189. Just like the square and the square root here, kind of. That one comes out absolute value. It's the absolute value of 189, which is the same thing as 189, right? Good? Did that bring you back some memories? Same trick problem? Okay. So that was the square root. Now we have a notion not only of taking the square root of just numbers, but we also have the square root notion of taking the square root of monomials. So to take a square root of a monomial, that's a perfect square, you take the square root of the numerals, which are just the numbers that show up in the term, and divide the exponents of the remaining terms by 2. So let's take the square root and then read that again, and then I think you'll see how it makes perfect sense. So if I want to take the square root of this thing, how do I do it? Well, what's the square root of 16? 4. So that was, we took the square root of the numeral, 16 was our numeral, we took the square root, and divide the exponents of the remaining terms by 2. So here's our remaining terms, we divide their exponents by 2. So 4 times x to the 1 times y to the 5. Everyone follow that? Notice that if we were to square this, take this and multiply it by itself. If we were to take that and multiply it by itself, 4 times 4 would give us 16. X times x gives us, when you multiply terms, you add exponents. 1 plus 1 is 2. Times y to the 5 times y to the 5, add the exponents is going to be y to the 10. So you square that, you get that, you take the square root of that, you're back where you started. Good? No questions on that? Okay, so now we got a little bit warmed up. Let's do the next one. Tell me what to write. What's the numerator?
10a to the 3.
Oops. 10a to the 3. Okay.
Over 3x squared y to the 4.
Wonderful. Someone who's not Peter.
5x
Oh man, this is my
and y to 5.
All right, now someone else.
I can't read that first one.
That's 4 over 49.
2 over 7.
2 over 7. Why do you sit on the back row if you can't see?
That's a good question. X to the 2 times w to the 3.
Good. Make sense to everyone? Nothing weird going on? Cool. All right. Now we have a notion of multiplying polynomials together. So we can multiply polynomials together, and it's almost identical to already how you do, I don't know what you call it. Is that called like long multiplication or something like that?
Yeah.
Just multiplication, something. It's almost identical to how you already do multiplication. So let's go over an example of how you're used to doing multiplication. So we're doing 213 times 21. With me? How do you typically do this? You typically say Well, 1 times 213 is just 213, right? And then you do a placeholder when you go to the 2, so you put a 0 there. 2 times 3 is 6. 2 times 1 is 2. 2 times 2 is 4. And then you add those together, and you get 4, 4, 7, 3. Right?
Yeah.
Pretty standard process? Okay. Turns out, when you do multiplying polynomials together, you do almost the exact same thing. So I'm going to do this polynomial multiplied by this polynomial. Step 1, rewrite the polynomial so that the terms are in descending order. Good? And then, multiply it out. We do almost the same thing. I'm going to multiply the 3 to all those, and I'm going to multiply the 2x to all those, and then we're going to add them together. So 3 times negative 2 is negative 6. 3 times negative x is negative 3x. 3 times x squared is 3x squared. And 3 times 3x cubed is 9x cubed. So that was multiplying the 3 through there. Again, we do our plus 0 placeholder. 2x times 2 is minus 4x. 2x times negative x is negative 2x squared. 2x times x squared is 2x cubed. And then 2x times 3x to the 3 is going to give us 6x to the 4. Add it all together, and you get 6x to the 4 plus 11x cubed plus x squared minus 7x minus 6. Pretty straightforward? Okay. Similarly, we have a notion for dividing polynomials, and it's almost identical to the way you do long division. So going through our process here for long division, 259 divided by 17, how do we do that?
How many times does 17 go into 25?
You start, so how many times does 17 go into 2? It doesn't. So then you skip to here. So how many times does 17 go into 25? It goes into it once. Once times 17 is 17. Subtract. And 25 minus 17 is 8. Bring down to 9. How many times does 17 go into 89?
4.
Is it 4 or 5?
I think it might be
5. What's 5 times 17?
85.
Huh?
85.
85. Is that wrong?
That's right.
Okay. So 85. Subtract, what do you get? 4. Now what?
Remainders. Or just keep going decimals. If you
Now,
want to
yeah. Okay, so we're not going to go the decimal route. So you're back in 3rd grade before decimals. What do we do when we get to that 4? Yeah, we call that the remainder. Right? And so we represent this as it's equal to 15 plus 4 over 17, right? Or 15 remainder 4, same thing. Okay, so we're going to do something almost identical now, taking a quotient between two polynomials.
Okay.
So I got this quotient between two polynomials. Here's how we start out. So I got my 4x cubed. We only look at our highest order term here, and we ask how many times does that go into the term that we're currently looking at. So how many times does 2x go into 4x cubed?
2x squared.
2x squared. Because 2x squared times 2x is 4x cubed. That make sense?
Okay.
So, now we do the same thing that we did here. We said once, then we did 1 times that number, and then subtract it. So now I'm going to do 2x squared times this, and subtract it. Exact same process. So 2x squared times 2x is going to give me 4x cubed. And then 2x squared times 3 is going to be minus 6x squared, right? And now I need to... Are you good with that? Okay. And now I need to minus this from this. So if I'm going to minus this, that is a negative and that is a plus. Because I'm subtracting this from this.
Yeah.
So multiply it by -1 and then just add it. You with me? Okay. So now when you add those together, that and that is 0, and that is
Just negative 2x squared.
negative 2x squared, right? Repeat. How many times does 2x go into negative 2x squared?
Negative x.
Negative x? Yeah?
Negative x squared.
Negative x squared?
You're just gonna believe me?
No,
Negative
I
x.
think so.
Negative x.
Back to negative x?
It's negative x.
Anyone else have an answer?
That was right. Yeah.
Alright, it's negative x. Negative x times 2x gives us minus 2x squared, right? Oh, I forgot to bring down the minus 9x. Bring down the minus 9x. Same thing you always do. Same thing we did here, right? We brought down the 9. Okay. Anyways, so negative x times that gives me negative 2x squared. Negative x times negative 3 gives me
3x.
positive 3x, right? Now I need to subtract this from this.
What?
Did I do something weird? Negative x times negative 3 is positive. That's a plus 3x. Sorry, they're kind of overlapping. Plus
No.
3x.
Negative times negative makes it positive, but then you got subtracting.
I didn't do the subtracting yet.
Oh.
Notice that this is still the same term as that.
Yeah.
So if I'm going to subtract this from this, that's the same as adding this. Flip all the signs. So now add those two together. Negative 2, positive 2. Those cancel out. Negative and negative gives me minus 12x, right? Once again, bring down the plus 7. How many times does 2x go into negative 12x?
Negative 6.
Negative 6 times. Negative 6 times that gives me negative 12x plus 18, right? And now we need to subtract this from this. So flip the signs. Make that one positive, make that one negative, and add them together, and what do we get? That comes out to 0. Sorry, that's a minus 18. And 7 minus 18 is?
Negative 11.
Negative 11. And that's our remainder. Right? Because 2x doesn't go into negative 11.
Yeah.
So we're done. So our answer now is, let me write this just very explicitly. So we just really found that 4x cubed minus 8x squared minus 9x plus 7 all over 2x minus 3 is equal to 2x squared minus x minus 6 minus 11 over what we were dividing by, 2x minus 3. You follow that? That's the answer we just calculated. Anything weird there?
No, that makes sense.
Okay. So that's how we calculate a quotient of polynomials. Now, a few properties here. Go through each one of these. Common products that we use over and over again. So if I have a times x plus y, this one's just flat out the distributive property, that's ax plus ay, right? So now property 2, let's write this one out. So I have x plus y times x minus y. What's that equal to? Well, rather than writing it in a table like this, notice that another way that we could do this in our heads is we could have said that's 1 times 213 plus 20 times 213, and then add the numbers together, right? We can do a similar thing here. I can do the x times x minus y, and then the y times x minus y, and just add the results together. So when I do x times x minus y, what does that give me? If I distribute the x into here, then that gives me x times x is x squared, x times negative y is minus xy, right? And now I need to distribute the y into each of those. Y to x gives me a plus xy. And then y to negative y gives me, what's y times negative y?
Y.
Negative
Negative.
y?
Negative y squared.
Squared.
Negative y squared.
Negative y squared. So we have a stupid thing right there. I'll write along the minus sign. Minus negative y, or minus y squared, right? Now notice, negative xy plus xy is 0. And so the whole thing is equal to x squared minus y squared. So that's this property. X plus y times x minus y is x squared minus y squared. And it's important to get used to think about these properties backwards. X squared minus y squared can be rewritten as x plus y times x minus y. When we go backwards, we call that factoring the term. And this is one that we use a billion times all throughout math. We often refer to that as a difference of squares. You can always factor a difference of squares. Why is it called a difference of squares? Because it's a difference of squares. Okay.
Are these like theorems?
They're theorems. Sure, you can call it a theorem if you want. They're just common products that show up a lot. And so they're things that most people doing math kind of just do. They get so used to it, they don't really think about it anymore. Like if you ask me to calculate now, something like, if you ask me to calculate like x squared minus 81, I instantly think in my head, that's x minus 9 times x plus 9. And that's using this, right here. I have something squared minus something squared. Notice that this is the same thing as x squared minus 9 squared, right? If you ask me to factor that, it's x minus 9 times x plus 9. That's just using this exact thing right here. And it's almost something you don't even think about. It's just so automatic. You get so used to it. So these are common products that everybody just gets used to. That nobody really goes through all the pains of re-multiplying those out every time. So that's what we mean by they're common products. But we'll try to get you really familiar with them, which is why I'm explicitly writing all these out. Okay, a plus b squared, let's look at that one. A plus b squared is equal to, now that's a plus b times a plus b, right? So this is the same thing as a plus b times a plus b. And so now I distribute the a through to both those. That's going to give me a squared plus ab. I'm distributing this to that and this to that. Now I'm going to distribute the b to both of those. B to that gives me plus another ab. And b to that gives me plus b squared. My equal sign right here. Right?
Okay.
Which is equal to, we have an a squared, plus we have an ab and an ab, which is 2ab, plus b squared. Right? And so, common example of where you might see something like that, commonly you'll see something like, what's x plus 3 squared? You're going to get used to saying instantly. You're just going to write, oh, that's x squared plus 6x plus 9. And you're just going to do it in your head. It's this term squared plus 2 of the product of these two terms plus this term squared. So that squared plus 2 of those plus that squared. And that's what everyone thinks in their head when they write out a product like this, once you get used to them. Okay, next common product. A minus b squared. Well, that's basically the same thing. A minus b squared, what's that equal to? Well, we get the a times a, gives me a squared. I get the a times minus b, that gives me minus ab. I get the minus b times a, that gives me minus ab. I get the minus b times minus b, gives me plus b squared. So that's a squared minus 2ab plus b squared. Follow that? All right?
Yeah.
Next one, x plus a times x plus b. X plus a times x plus b is equal to the x times the x gives us an x squared. A times x gives us ax. X times b gives us bx. And a times b gives us a times b. Finally, let's do our last one. The last one is we have ax plus b times cx plus d. Right? And so that's equal to ax times cx is going to be acx squared. That's those two multiplied together, right? Plus, let's see which one I write next, this one. So then I'm going to distribute this to this. So I did this to this, now I'm going to do this to this. That's going to be plus abx plus, now I'm going to do this to this, that's going to be bcx, plus now I'm going to do this to this, which is going to be bd. which is exactly what I have written right there. So common products going from this to this is multiplying them. Another thing we're often interested in is factoring terms, going from this side to this side. So when you're multiplying, you go from here to here. When you're factoring, you go from here to here. Factoring meaning to rewrite it as a term of products. Any questions on any of those before I move the camera? Okay, so let's move the camera and do a bunch of examples. Let's see. Cool. Got the rest of my board. Will let me do this. Okay, I want to turn on the brightness. Won't let me. Let me know if that camera starts dying. Okay. So just a bunch of examples now. So multiplying this out, 3x plus 2y squared. Tell me what to write.
9x squared.
9x squared.
Plus 6xy. Plus 6xy. Plus 4y squared.
Perfect. And then obviously we combine the 6y's together, so 9x squared plus 12xy plus 4y squared. Right? And you could have been given the opposite problem. You could have been given this and been told factor this. If you were given this and told to factor it, that would be take that and rewrite it like that. Good? All right. Not Jeremy 2.0. Not Chandler, I mean. What's this? Tell me what to write. Let's go, Celesta.
6x squared
Good.
plus, is it 4x h?
Sure, but you're at the H first. Alphabetical order.
Minus 21hx minus 14h squared.
Good, which is obviously equal to 6x squared. We have 4 here. We have minus 21 there, which gives us minus 17hx minus 14h squared. Right? Okay. What about something like this? What are we going to do?
Just do two and then do it together.
Yeah, just start out by combining 2 terms, and then you'll be left with only 2 terms after that you can combine again.
Yeah.
So which 2 should we combine first? These 2 or these 2?
The first two.
Which one's first? Is this one first or this one first?
This one's first.
Left, right.
So combine these 2. So the second option is the first 2. Okay. I said, should we do these 2 or these 2? And he said the first one.
Oh.
Which is why I was confused. Did you mean first is in the ones I pointed to first, or first is in left to right? You guys all seem to be on the same page. All right, so these 2 first. Good choice. Why is that a good choice? Because when we multiply these 2 together, then we're going to end up with some to the power of 4 term like this thing has. And maybe we'll be able to notice some trick then.
Yeah.
So,
Isn't there a trick with that first one though?
with this one,
Yeah.
there is a trick with this one. What is it? Notice that this has a form. We have a minus b times a plus b. Those 2 are the same. Those 2 are the same. The only difference is a sign there. What is a minus b times a plus b equal to?
It's equal to a squared plus b squared.
That's a difference of squares. A squared minus b squared, right?
That's right.
Looking back over here,
That's what I was looking
told you, this one comes up super frequently, all the time. So, these 2 right here, that's just going to be this term squared minus this term squared. So this is equal to, this term squared gives me x to the 4 minus this term squared. Negative 2y squared is what?
4y squared.
Just 4y squared. Right? And then we still have this term, x to the 4 plus 4y squared. Everyone follow how I combine these two into just this? Anything weird happen there? We can write that out more if we need to. Everyone see it? Are you just looking ahead? Or are you still trying to see it?
Is your b a negative or a positive? What's your b? Is it negative 2y or is it positive 2y?
Oh, it's just 2y, right?
Yeah, you're right.
Because this is a minus b, a plus b, so a squared minus b squared. So I did say b wrong. I said negative 2y squared. I should have just said 2y squared. Okay, so on the same page. Okay, wonderful. Now what can we do with those two?
Difference of sums, or difference of products, squares.
It's a difference of squares again.
There it is.
Once again, we have the same thing and the same thing. The only difference is a minus and a plus. This still has a form a minus b and a plus b, right?
Yeah.
So it's just going to be that thing squared minus that thing squared. So it's just going to be equal to x to the
8.
a minus
8.
8
No.
square 4,
Oh,
16
2, 4.
y to the 4th. Perfect. Good on that? All right. So there was a bunch of examples. Now skipping to a next section. Next section we talked briefly about primes. Intuitively, what's a prime number?
No, you can't divide besides by the one itself.
It can't be divided evenly.
Can't be divided by
No,
any
that's
number.
not one.
Can't be divided by any number but 1.
It's
And itself.
LCM.
And itself.
Is its base itself. I don't know. What are you looking
It can only be divided by 1 in itself.
Yeah.
Question, is 1 prime?
No.
It can only be divided by 1 in itself.
for? It is prime.
It's not. Didn't we prove in discrete that it's not prime?
Okay, so let's go over what prime number is now.
Okay.
Prime. An integer is said to be prime provided that it is greater than 1 and its only positive integer factors are 1 and itself. So is the number 1 prime?
No,
Why not?
because it's not greater than itself.
It's not greater than 1. Every prime number has to be greater than 1. Is 2 prime?
Yes.
Yes, no, yes?
Yes.
Yes. What can you divide it by? 1 and 2. 1 in itself. Is 4 prime? No. What about 5?
Yes.
What about negative 5?
Yes.
No.
No, it has to be greater than 1.
Has to be greater than 1. No negative numbers prime. Okay. Think you got a good feel for it, right? Now, factors of a number. You already have good intuition for what a factor of a number is, the things that go into it evenly. But just to be super clear, I want you to tell me what the factors of each of these numbers are. So what are all the factors of 12?
4.
3, 4, 2, 6. 1.
Wow, let's do it in some sort of order. 1, 2, 3, oops, 3, 4, 6, right? 12. Those are its factors. Wonderful. What are the factors of 36?
1, 2, 3, 4,
6.
12.
Oh, skip.
9.
9,
12.
12,
18. What's it? 18.
18,
32. 36.
36. That's a 6. Okay. Now, notice that they always come in pairs. 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. Pairs. Unless there's an odd number of them. Same at the 12, 1 and 12, 2 and 6, 3 and 4. Okay, factors of 9.
1, 3,
Factors of 11.
111.
1 and 11. Okay, we found a prime number. Its only factors are 1 in itself.
Sweet.
29. 1 and 29. That's it? You're telling me that's prime? What about 31? Bold. What about 33?
1, 3, 11, and 33.
Good. So prime, prime, prime. The rest not prime.
That's right.
Yeah.
Good? Now, we have a notion of representing a number, even if it's not prime, we can represent it as a product of its prime factors. A product of its prime factors. Is that something you're used to doing? Representing? Are you confused by what I'm even saying?
Yeah.
Okay, so let's do it with the number 12 really quick. 12 is equal to, what are the factors of 12?
1, 2, 3, 4, 6.
If you were to factor this number, what could you factor it into? What's two numbers that multiply together give you 12?
1, 2, 4.
I could do 1 and 12, but that doesn't really get me anywhere, right?
3 and 4.
But you're right. I can do what?
3 and 4.
3 and 4. Perfect. 3 and 4. Can I split 3 up anymore?
No.
What about 4?
2.
I can represent it as 2 times 2, right?
Yeah.
Can I split 2 up anymore?
No, that would be no.
Can I split 2 up anymore? Can I split 3 up anymore? So we factored this number as much as we can. And notice that all the factors we reduced it to are prime factors. If any of them weren't prime, we could split it up more. So this is 12's prime factorization. 3 times 2 times 2.
Yeah.
Let's do another one. Let's write 36 as a, let's write out its prime factors. What goes into 36?
6 and 6.
Yeah, we can think about 6 times 6. Can we split up that 6?
Yeah.
Can we split up that 6?
Yeah.
So what should I write here?
3 times 2 times 2 times 3.
3 times 2 times 3? Is that what you said?
3 times 3 times 3 times. Oh, 3, yes, that.
3 times 2 is?
6.
2 times 3 is? 6 times 6 is? Okay, now typically how we write out these prime factors is we write this as, this is 2 squared times 3 to the 1, and this now is 2 squared times 3 squared. Just to clean it up.
2 first instead of the larger number.
You could do it in descending order or ascending order. Completely a matter of preference there. I just typically do ascending, same reason that I write A before B, not B before A. It's just a matter of convention. Make sense? So any number we can represent as a product of its prime factors. Anyone from discrete math remember what that's called? The theorem that we use to prove that?
For what numbers?
To prove that every number has a prime factorization. Remember that? I guess you're the only one now.
Yeah.
That was called the fundamental theorem of arithmetic. And it was a big pain to prove.
Yeah.
Took a lot of work to prove. Not every number has a prime factorization, but it's pretty intuitive and very helpful to know that. Because this is often how you reduce massive fractions.
Massive fractions.
Yeah, so give you an example. Let's say that I had 1024 divided by 1536. And I want to reduce that. I think about it in terms of its prime factorization. This one right here, I happen to know that's 2 to the 10. This one down here, that's 2 to the 9 times 3. Cancel out, leaves me 2/3. Because 9 of those 2's cancel out with 9 up here, leaving 1, 2 in the numerator, 3 in the denominator. Make sense? So, common trick when you're trying to reduce fractions, you try and write it in terms of its prime factorization, and then it becomes real obvious what exactly can and cannot cancel out. Okay, so the same way that we have a notion of prime numbers, we have a notion of prime binomials. And a prime binomial is one that you can't factor anymore.
Okay.
That's the intuition guiding you. You with me? With the intuition, we'll do some examples, but that's the intuition. So here's one that's not prime because we can factor this. Let's factor this in. Can I factor anything out of those two terms?
Is that a 4?
Yes. Those are both 4s. That's an x, that's a 4, that's a b, that's a 2, that's a 2, that's an x.
Oh, thanks.
Minus sign, equal sign.
Well, okay, you factor the 4s.
You can factor the 4s, is that it?
And squares.
The 4x squared from both of them, right? So when I take 4x squared out of this term, so I can write it as 4x squared times, if I take 4x squared out of this, what am I left with?
X squared.
X squared, right? Because x squared times 4x squared gives me 4x to the 4. And if I take 4x squared out of this, what am I left with?
B squared.
B squared, right? Can I factor this anymore?
Yes.
Yes.
What does it factor to?
You can use your common products number 2.
Yeah, this is going to be x minus b and x plus b. That's a difference of squares. We use that one all the time. Right? And so, this is a prime binomial. There's nothing else we can factor out of this. This is a prime binomial. There's nothing else we can factor out of this. This is a prime binomial. There's nothing else we can factor out of this.
Well, you could of the x's. Go 4 times x times x.
I can't factor an x out of this term because that doesn't have an x.
No, 4x squared. How is that prime?
Oh. If I factor out the x, I see what you're saying. You're like saying factor out of this term, so you want this 4 times x times x.
Yeah, because it's not prime.
It is prime because that still ends up the same term, the same factor.
The whole thing ends up the same thing though.
Yeah. So if you factor it out and it's not a sum or a difference anymore, we keep that all together as one term when we're factoring these binomials. So we don't split this up into more. We leave it as just one.
Okay.
And then these ones we actually can't take anything else out of, right?
Yeah.
So leave single terms alone. Single terms, you want to combine as much into single terms as you can. And then these ones, factor out as much as you can. So, note here, something else that you might have been taking issue with. So that's one thing you could take an issue with. Another thing you could take an issue with is, why is something like this prime? Why can't I write this as the square root of x plus the square root of y times the square root of x minus the square root of y? If I were to multiply this out, I would get that again. That's true. But we still count this as prime because these aren't binomials.
Binomials?
Yes, because their exponents would be 1/2. A binomial has to have integer exponents.
Oh.
Positive integer exponents, right? You remember back talking about polynomials? So this is not a polynomial. X to the 1/2, not a polynomial.
Okay, yeah.
So that's why we don't reduce it to square roots.
Did you say polynomial or binomial?
A binomial is a polynomial with 2 terms.
2 terms being x and b.
So a binomial is just a type of polynomial. The same way that a square is a type of rectangle.
Isn't it a quadratic polynomial? Is a binomial?
A binomial is a polynomial with 2 terms.
Isn't that the same thing as a quadratic?
That's not a name of one. We don't call it a quadratic polynomial. You're probably thinking of the quadratic equation.
Degrees.
Huh?
When you're doing it to the degrees of something.
A quadratic is something, okay.
Right?
Quadratic equation is the equation with a second degree polynomial is a quadratic. Quadratic means your exponent is 2. Polynomial means you have 2 terms. So the exponent, the highest exponent on this is 1. But there's 2 terms. There's the x term and the b term. So it's a binomial. but its degree is 1. It's a first degree polynomial. Here's a quadratic. But this is not a binomial because it has 3 terms.
That'd be a quadratic trinomial.
Yeah, you could call that. So quadratic refers to the degree. Binomial is talking about how many terms are actually in it. Okay. There we go. Okay. Some more prime binomials. Or just prime polynomials in general. Not necessarily binomials. X plus y, that's prime. Can't factor anything out of it. X squared plus y squared, that's prime. So a difference of squares is not prime. You can factor that. A sum of squares is prime. You cannot factor that anymore. So we're very happy when we see a difference of squares. That's very nice in math when those come up. When you see a sum of 2 squares, you're angry. We don't like that. Alright, here's another weird one that's prime. Can't factor anything out of that. There's no way to represent that as a product. And here's another one that's prime. So there's lots of things out there that we can't factor anymore. Whereas factors are going to get their prime order. And that's what we essentially mean by prime. There's no more nice way of factoring that. Good? Alright. So tell me how to factor this, or tell me that it's prime if it can't be factored. X squared minus 9. Is that prime?
No.
So it can be factored?
Squares.
It's a difference of squares. We can think about this as x squared minus 3 squared, right? And so what's it equal to?
X minus 3.
Well, x squared minus 9, but we want to factor it now. So it's going to be x minus 3 times x plus 3, right?
Yeah.
Remembering back to the way that you were probably taught to factor these things, maybe also show that in case that's helpful to you guys. You were often taught, okay, if I need to factor something that's squared, that's going to have 2 terms in it. So we write terms like that. We put the x's first, and then I need to find 2 numbers that multiplied together give me this number, and added together give me the coefficient to the x's, which in our case is 0. So what 2 numbers add together give me 0, and multiply together give me -9. That's positive 3 and -3. I don't know, does that sound familiar?
Yeah.
Or is that not how you were taught? Just taking guesses. Anyway, that's how we factor. Okay, let's factor this one. Oh, that's a beast. How on earth are we going to factor that, what do we think? Once again, we can go back to the method you were taught early on. I know that this term times this term has to give me 9x squared. So what do we think these terms could be? 3x. And then whatever terms I put here, when I multiply them together, they have to give me this.
4z.
So it could be 4z, or it could be like a 2 and an 8, right? You with me?
No.
2 times 8 is 16.
Let's just throw that in there.
Okay, I was missing the z. Sorry, I thought you dropped z.
Oh, sorry. Yeah, so 2z times 8z also gives me 16z squared. Now we need, so that this number times this number, plus this number times this number, gives me 24. And 8 times 3 is already way more than 24. Or is already 24. 2 times 3, that's 6. You add those together, you get 30. So obviously we picked wrong, which we intentionally did to show you the wrong one. And now we'll go to the right one, which was 4 and 4. So when you put 4 and 4 in there, notice 4 times 3 is 12, 4 times 3 is 12, and so we're going to get 24xz. Make sense how we did that? And so finally we can write that as 3x plus 4z squared. And that's the most concise way we could write it factored. Good on that one?
Yeah.
Okay, next one. Oh, how are we going to factor that thing? Same basic strategy. The numbers multiplied together here have to give me this term. What gives me 15x squared? 3 and 5 do. So we can put a 3x here and a 5x here. That's our guess so far, right?
Yeah.
Our numbers here have to multiply together to negative 8. So what gives us negative 8?
Negative 2
Negative 2
and positive 4.
and positive 4. Negative 2, positive 4. And so now let's try it out. 3x times 4 is 12. So we have 12x minus 10x leaves us with 2x. And so we filled it in right.
Cool.
Good?
Then why didn't 2 and 8 work if 3 and 5 and 8? I don't know. Why did it have to be 4 and 1?
Well, there's a bunch of different ways we could do this. Notice that 1 and 8, if I did 1 and 8 here, negative 1 times 8 still gives me negative 8, right? But negative 1 times 5x is negative 5x, plus 8 times 3x is 24x. 24x minus 5x is not 2x.
So you just have to find the combination.
Yeah, you have, there's only specific numbers that work. There's not going to be a bunch of different numbers that work. So you need to find the unique numbers that work. In our case, that was put a 2 here and a 4 there, right? 12 minus 10. Good? Okay. Now cubes. Moving on to cubes. X plus y cubed is x cubed plus 3x squared y plus 3xy squared plus y cubed. Now we could multiply all that out. No point seeing all that algebra there. You would know how to multiply this out by hand if you wanted, right?
Yeah.
Notice the pattern here. We have x cubed, x squared, x to the 1, x to the 0.
Yeah.
Here we have y to the 0, y to the 1, y to the 2, y cubed. So the x's we decrement the exponent each time, and the y's we increment the exponents each time. With me?
Mm-hmm.
And then the coefficients are just 1, 3, 3, 1. And you just have to memorize that.
Which is the Pascals Triangle, right?
Oh, how many of you have heard of Pascal's Triangle?
Yeah.
Should we briefly do Pascal's Triangle real quick?
Yeah, that'd be cool to do.
Alright, we'll do Pascal's Triangle. Which is tricks for coming up with the coefficients here. 1, 3, 3, 1. So for example, maybe, we don't need this stuff up here anymore. Maybe motivate Pascal's Triangle a little bit. Imagine that I were trying to figure out x plus y to the 5. Now who wants to multiply all that out and add up all your terms? How many terms would I have if I multiplied all that out?
6.
32.
32.
I would have 32 terms. This blows up absurdly fast.
Yeah.
Maybe we should have done the cubic really quick just to make you see how annoying it is to do this by hand. So x plus y, just with the cubic, we're already going to have 8 terms. So x plus y cubed is the same thing as x plus y times x plus y times x plus y, right? You with me so far? So I'm going to multiply these two out, and then we'll do this one last. So I have x plus y. I'm not going to do this one yet, but I'm going to multiply these two out. When I multiply these two out, I'm going to get x squared plus xy plus another xy plus y squared. Right? And now I need to distribute x into each of those terms, and then y into each of those terms, and add all those up. So when I distribute through the x, that gives me x cubed plus x squared y plus x squared y plus xy squared. That was distributing the x through all those. Plus now distribute the y through. We get x squared y plus x cubed. Oh, I'm distributing the y. Confused myself. Distributing the y. Okay, x squared y plus xy squared plus another xy squared plus y cubed, right? And now add them all up, and what do we get? We get 1x cubed. We get plus how many x squared y terms? X squared y, x squared y, x squared y. We have 3 of those. Plus 3x squared y. Plus, how many xy squared terms do we have? Xy squared, xy squared, xy squared. 3 of those. Plus 1 y cubed term. Okay, there's doing it the stupid long way, right? Now imagine I took this thing and I multiplied it by x plus y again. And then multiplied it by x plus y again. You see how that's blowing up? And so by the time I put a small number right here, like 15, you're going to be spending an hour multiplying all that out.
At least, with 15 terms.
Yeah, even if we just do 10 terms, and if you do it the stupid way and never combine like terms, you're going to have 1,024 terms that you need to combine. Right? 2 to 10, 1,024. So, Pascal's triangle helps us do these really, really quick. So let's go over Pascal's triangle and then see how it helps us with these problems, and then go back to the problem. So Pascal's triangle, ton of applications for it. It's amazing how often it shows up, but Pascal's triangle, we start out with a 1. And then, to the left of it, you add up all the numbers. You kind of need to see the pattern getting going, so I'm just going to write the next row. It's 1 and 1, because 1 plus 0 is 1, and 1 plus 0 is 1. I know that seems weird, but with the next row, it will seem better. Now for the next row, 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 0 is 1. Now for the next row, 1 plus 0 is 1. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 0 is 1. You see the pattern? All right, so what's my next row going to be? Tell me the numbers.
4, 1.
Perfect. Next row.
1, 5, 10, 5, 1.
Okay, so now we'll call that enough. We sometimes call this the 0th row. We call this the first row, this the second row, this the third row, this the fourth row, this the fifth row. With me? Now, if I want to calculate x plus y to the 5, it turns out the coefficients are going to be the numbers on the fifth row. So I have 1 times, and I start my x to the max and my y to the min. X to my max exponent times y to my minimum exponent, which is 0. Or in other words, this is just x to the 5. But I want you to see the pattern. Plus, next number, 5 times, x goes down 1, y goes up 1. X to the 4, y to the 1. Plus next, 10 times x to the 3, y to the 2. Plus next, 10 times x to the 2, y to the 3. Plus 5 times x to the 1, y to the 4. Plus 1, x to the 0, y to the 5. And that's the answer. And that's a lot easier than multiplying out 32 terms. Building this little triangle. That little triangle is called Pascal's triangle. And so this is a shorthand that almost everyone uses to quickly calculate these things for things like x plus y to the 5. No one remembers that. And even this equation, I don't even remember that. I always just think back to this triangle, because it's real easy to think about this triangle to this row. 1, 3, 3, 1. It's pretty easy to just see that triangle in your head and do it, even for a cubic. Notice how this holds for all numbers. So really quick, x plus y to the 1, what's that equal to?
X plus y.
It's just x plus y, but using our formula, it's 1 times x to the 1 times y to the 0, plus 1 times x to the 0 times y to the 1, which is still just x plus y, right? So it still works. And notice, what's x plus y to the 0? 1, which is what that is, 1. So that's why we call that, that's why we start counting from 0 rather than start counting from 1 with Pascal's triangle. And it makes that relationship holds nicely. Make sense?
Yeah.
Mm-hmm. Okay, so there was a little side note with Pascal's triangle, which is very useful for multiplying out these factors. Now, for those of you who go and take algebra classes in school, you have that cheat to jump ahead. Because usually your teachers want you to struggle with this before they show you that. So now you don't have to struggle. But if you want to struggle, here it is for a cubic. You can just memorize that if you want, if you hate Pascal's triangle for some reason. Now, Pascal's triangle, really, really cool. If you replace the plus with a minus, the numbers come out the exact same using Pascal's triangle. Now you just alternate between positive, negative, positive, negative. Okay. So for example, if we were doing x minus y to the 5 once again, but this time with a minus sign in there, then that would have been x to the 5. Now we do minus, let's see, what was it, 4 times x to the 4 y plus 10 times x cubed y squared minus 10x squared y cubed plus 4x y to the 4 minus y to the 5. It was 5s?
It's right below what you're writing.
Oh, I literally have it written right in front of my face. Make sense? Okay, so Pascal's triangle, a billion times better than memorizing these formulas. But there's the formulas. Okay, so now let's multiply this thing out. 2a plus b cubed.
Okay.
Now just blindly using the formula, that's going to be 1 times x cubed. So we have x cubed plus 3 times x squared times y plus 3 times x times y squared plus times b cubed. Right? And now you can rewrite that as, I don't know why I didn't leave any space to do it. And now we can rewrite that as that's equal to, this term then becomes 8a cubed, plus here we have 2 squared is 4 times 3 is 12, 12a squared times b plus 6ab squared plus b cubed. Everyone follow what I did there? Nothing weird? Okay. Like powers. Like powers, which is when they both come to the same exponent. And I think it's the case that if it's a difference and they come to the same exponent, then you can always factor out an a minus b. And if it's odd, an odd exponent, and it's a sum, then you can factor out an a plus b. Notice that sometimes when you have a sum and they're the same exponent, you can't factor it. For example, a squared plus b squared can't be factored. But if it's a difference, it can always be factored, which is why we like the differences. Okay, so let's do some more factoring. Or are we multiplying on this? It's probably just writing the things out there. I'm not sure what we were supposed to do here. Because that seems like we're supposed to factor it. Like powers. Addition of fraction, the sum, like powers. So this one, we're doing it backwards. So this, not factoring it, but multiplying this out. So here we're multiplying it out. And what do we get? You could multiply that whole thing out if you wanted to. Or you can see how this fits the same form as right here. If we replace a with a, so a is a and b is just 3 here. You see that? This has the same form as this. If we replace all our 3's with b's, then these now have the exact same form. So what does this equal? If I were to multiply that out and add all my terms together, what would I get?
A to the 3 minus 27
minus 3 to the 3, which is the same thing as a cubed minus 27. Right? Okay, so that's what we were supposed to do on that one. Now for these other ones, we're factoring. So let's factor this one. How can we factor this one? 27x cubed plus 8y cubed. Can we even factor that? Is that 2 cubes? So this can be rewritten, that's cube runner. This can be rewritten as 3x cubed plus 2y cubed, right? And now we can just look at the formula. So now here's our a, here's our b, and we know now if we were to factor that, we would get with the sum, we get a plus b, so 3x plus 2y, times, and then we have a squared minus ab plus b squared. So a squared minus ab plus b squared. And that's how it factors. And this is prime, can't be factored anymore. Good? Okay. Next. We need to factor this thing. How on earth can we factor that? We can go back to the basic strategy now. So I need to find two things that multiply to be this. What's going to be my term here and here?
Your y.
Y?
Y3.
Y cubed.
Y cubed, sorry.
Yeah, if I put a y cubed here and a y cubed here, notice that y cubed times y cubed gives me y to the 6.
Yeah.
So we're off to a good start. Now I need two numbers that multiply together to give me negative 216, and that added together give me negative 19. Right?
Well, what's the square root of 216?
Does 216 have a square root?
I don't think it does.
So that doesn't work. When in doubt, you can always use
Calculators.
the Chandler method, or was it the Jeremy method? I don't remember.
Which method is that?
Divide
216. Okay, 216, that's the same as what if we divide it by 2? So that's the same thing as 104 times 2. 108 times 2. Okay, can we do anything else with it?
Yeah, you can divide it by 2 again.
We can divide it by 2 again, which gives us 54 times 2 times 2, right?
Again.
Again, what's 54 divided by 2?
27.
27 times 2, we'll just say cubed now.
Oh, so 3 cubed times 2 cubed. Right?
Yeah, that's what we done.
So 3 cubed times 2 cubed is what that is. So I need two numbers now that multiply together to be this. So I got to split those 3's and 2's into two separate factors.
Oh, so just 3 cubed and 2.
So I can do 27 and 8 if I want, which is the one I want. But I could have also done something like 6 times 36, if I did that right.
Yeah, but that wouldn't have worked for your second term.
It wouldn't have worked. The one that happens to work is 27 and 8, but I just don't want you to think putting all the 3's in one term and putting all the 2's in another term is how you were supposed to do it. It's an accident that that happens to work in this problem.
But it's the only way that does work in this problem.
Yeah, there's always only one way to make it work. So yeah, you can't just do whatever you want. I just want you to make sure that it's an accident that it's the easiest answer for us. Okay, so in our case, 27, tell me how to write it. Is it negative 27 or positive 27?
Negative.
And does it go over here or over here?
Over there.
Doesn't
Wait, it doesn't matter.
Alright, and then we have the plus 8, right? So negative 27 times positive 8 is negative 216, right?
Yes.
Double check that in your head. Yeah, it comes out.
Okay.
And then negative 27 plus 8 is negative 19. Right?
Yes.
So are we done?
Yeah.
Is that as factored as it gets?
No.
No? What else can we do?
Y times 2 times 2 times 2.
Let me rewrite our answer there.
Or y plus 2.
We have y cubed plus 2 cubed times y cubed minus 3 cubed. We have a sum of cubes and a difference of cubes. Those can definitely be factored more.
Yep.
We're not even close to done.
Why?
We're factoring it as much as we can until we only have prime terms. This is not a prime factor. This is not a prime factor.
Oh, yeah.
You can get rid of all your cubes.
Be careful what you do. We can use those two formulas over there. We can't somehow cancel out any cubes. I can replace my difference of cubes using this formula, and I can replace my sum of cubes using this formula.
Oh, I see.
And so that's going to be equal to, notice from this term, I'm going to get a plus b. So a plus b, and then I'm going to be left with a squared minus ab plus b squared. And then we have times when we factor out this term, we're going to get an a minus b times a squared plus ab plus b squared. So factor into 4 terms, and now each of those are prime.
Okay.
Make sense?
Yeah.
Okay. Yeah, so don't give up too early just because you found numbers that come out nice. Alright. Let's try the next one. How can we factor this one? It's a single term, so it's kind of already done. The only other thing we could really do to this is we could represent this as 2 times a squared times b squared cubed. It happens to be a perfect cube.
Oh, I see. Because it's one term. Okay.
Okay? What about this term? X to the 6 minus y to the 6. Uh-oh, we don't even have a formula for that. What are we going to do?
Just
To the 6. How do we do it when it's to 6? Remember the binomial, or no, later we'll call it the binomial theorem, but this whole thing we were talking about with Pascal's triangle, that was x minus y to the 5. That wasn't x to the 5 minus y to the 5. Very different. So for something like this, you cannot use Pascal's triangle if you were tempted to think that way. So we have a 6 there. What can we do?
Can't you take out the x and y, like you did the a and b and a cubed minus b cubed?
Take out an x minus y?
Yeah, and x minus y.
I could take out an x minus y out of that. I know I could do that. Figuring out what's left over then is going to be a huge pain. Because how would I have to figure out what's left over? I would have to do a bunch of division. I don't even know if you know how to do this division yet. X squared minus y squared, or y to 6. I would have to divide that by x minus y, and that's going to have a bunch of terms in it. So it would be a mess to do it that way. We could do it that way, but it would be a mess. We want to just use our formulas if we can.
Okay.
What else could we do?
Are you sure that's not simplified all the way?
Could you
Positive.
take it all out by squares and then just have the cubes left over?
Not sure what you mean.
What if you just did it like put those in the parentheses, plus parentheses, and then square them?
Yeah, we could do x squared cubed minus
Square them.
y squared cubed.
I was gonna-
Now it's a difference of cubes.
Mm-hmm.
And now we can just use our formula.
Oh, I see.
And so now that's equal to, when we write it over here, using our formula. Let's see, which one we're using that formula. So we get a don't let me accidentally use the wrong one. We get a minus b, right? So that's x squared minus y squared. A minus b times a squared plus ab plus b squared, right? Okay, now can we factor that?
I want to say yes.
What's screaming to be factored in there?
The 2's.
I know what you mean by the 2's.
They're all divisible by 2, the exponents are.
No, you can't just factor out exponents like that.
Difference of sums.
Difference of squares. Anytime you see difference of squares, instantly you're thinking, oh, we can factor that. So that's x minus y, x plus y, times x to the 4, plus x squared y squared, plus y to the 4. We're always happy when we see a difference of terms like that.
Wait, isn't it x minus y to the squared, not x squared minus y squared? Like, aren't those two different things?
No, because you can go front and back. That's the final.
I'm not sure what you're saying.
So
This is the difference of squares.
look at number 2 on his common products.
Yeah.
Is he's doing the right to the left.
Oh, I see. Yeah, I see what you're getting at now.
Okay.
That makes sense.
Jeremy understands you. Yeah, I'm lost by what you're saying. Okay. So now let's look at that last term. What can we do with that last term?
Well, you can do the same thing. You can do x cubed to the cubed plus y cubed to the cubed.
Correct. Sorry, I just want to find where we are in here. Make sure I'm doing everything that could be done. Yeah, that's my thought. Didn't think about this one very smart. So coming back to this one, we kind of did it the stupid way, because this can actually still be factored. And you don't want to have to think about how to factor that, right?
That can be factored.
This thing can also be factored, but you don't want to have to think about how to factor that. I don't want to have to think about how to factor that. And the solution is we were stupid in how we wrote it over here, and we should have did what Jeremy said. We should have rewritten this as a x cubed squared minus y cubed squared. And if we would have written it that way, okay, now it's a difference of squares. We use our difference of squares formula. And so that's going to be x cubed plus y cubed times x cubed minus y cubed, right?
Yes.
And now, those are both a sum of cubes and a difference of cubes, and then I can use my cubic formulas for each of those.
Wow.
And so for this one, then we get, then you know how to plug it into these two formulas, right?
Yeah.
No point in you rewriting that out. So that's how we should have done that one. I was going to say that thing looked like it factored, but I didn't see how it was obvious. Anyways. Okay, so now coming down to this one, like you guys were already saying, you already have the right idea. You said think about this as x cubed cubed plus y cubed cubed, right? And now we can view it using this formula. And so that's going to be, it's equal to x cubed plus y cubed, a plus b, times a squared plus, or minus ab plus b squared. Did I do that right?
Yeah.
Good? Okay, and now notice that this is a sum of cubes, so we can factor it again. Why did I put an a there? That's an x. Come on, guys. Okay, so now we can rewrite the sum of cubes. That's going to be x plus y, times x squared minus xy plus y squared and then times this whole thing still. X to the 6 minus x cubed y cubed plus y to the 6. See if I can find that problem. Yes. Okay. No mistakes.
Nice.
Okay, so we did all those examples, did like powers. Next, we get to adding and multiplying fractions together. So, yeah. So, you ready to pay attention this time?
Now we can start.
What? I haven't paid attention this one.
Oh, okay. When you just said now, you need to pay attention.
I just said no, I need to focus.
Ah, you were paying attention, you just weren't focused.
Yeah.
Exactly.
Alright. So, lowest terms. When we're working with fractions, always and forever, we want to write it in its lowest terms. What do we mean by the lowest terms? We mean try to factor the numerator and denominator and see if there's any common factors you can cancel out. Right?
Okay.
So, rewriting the numerator of this, can I factor that numerator?
Yes.
Yeah, what is it?
X plus 3 times x minus 3.
X plus 3, x minus 3. And our denominator, can we factor that?
I would assume so.
We need to find two numbers. The terms are kind of written backwards. But we need these two together. These two multiplied together need to give us negative 2x squared. Sometimes we hate thinking about the negatives. If you hate the negatives on that 2 term, just multiply top and bottom by a negative number.
Okay.
So maybe before we write this, I'm just going to multiply the top by a negative, which puts a negative right there. There it is, right? If we multiply the bottom by a negative, it switches the sign on all the terms. So negative 2x squared becomes 2x squared. 2x becomes negative 2x. 12 becomes negative 12, right?
But the negative is still there, it's just on the 12.
It's there, but typically we don't like the x squared term to have negative in it. I don't know. If that didn't bother you, we didn't have to do this step. It just typically bothers students.
Move down for whatever.
Okay, so this is equal to negative. We have x plus 3, x minus 3. That's still the case. In the denominator now, we need to find two numbers. This term times this term have to give me 2x squared.
So just 2x.
We pretty much almost have no choice there. It's going to be a 2x and an x, right?
Mm-hmm.
Yeah.
Now my two numbers here, should give me more space. My two numbers here have to multiply together to give me negative 12. And when we add them, oops, there's an x there. And when we add them with the products of those, it needs to give us negative 2. So what do we think they are?
6 and
6 and 2 don't give me 12.
That-
Or 6 and 2 don't give me negative 12.
oh.
6 and negative 2 give me negative 12. Negative 6 and 2. Which one are you saying?
yeah, negative 2 and
Negative 2 and 6?
negative 6 and 2.
Okay, yeah, we can plug those in. Turns out that won't give us a negative 2 here, though. So, nice try. Try again. What else?
4, 3, 2, 6, 1, 4.
You forgot all the negatives.
Well, that's just the,
And then you need to tell me which pairs I'm putting in.
that's just possible.
What should I write right here? Good guess.
No, what?
Oh, that didn't work.
Okay.
How's that?
No.
No?
No, try again.
2 and 6.
Oh!
Yeah, it works.
Yeah, that works.
Negative 3 times 2x is negative 6. 4 times x is 4. Negative 6 plus 4 is negative 2. So that times that gives me negative 12. This times this is negative 6x. This times this is 4x. Add those together gives me negative 2x. 2x times x is 2x squared.
Couldn't you just factor 2 out at the very beginning?
You could, but then it's going to get uglier. If we factor out the 2, then, so we could have factored out 2 like you're saying, and then we would have had x squared minus x minus 6. And now I need to find the numbers to factor this into, right? And, oh, no, we could have.
Yeah, that would have worked nicely.
That would have worked nicely. Yep, you're absolutely right. And so now we could have rewritten this as, let's see, multiply together, give me that, add together, give me that. That's going to be -3 and +2. Yep, because up here we could have also factored out 2. And when we factor the 2 out of this term now, then that becomes a 2, and we get a 2 here, which is the same thing. Just slightly different order. Good. Good eye.
2 times. No, no, keep going.
Good? Okay, so here's our denominator, here's our numerator. Does anything cancel out?
Yes, your x minus 3.
Yeah, we have a common factor here, x minus 3, x minus 3. So we can divide top and bottom by x minus 3. And so now we're left with, we can redistribute that out if we want, and we can write this as x plus 3 over 2x plus 4. And that's what it means to write a fraction in its lowest terms.
That's its
Or
lowest.
to simplify a fraction.
Yeah,
Yeah, these were all its prime fact. This is its prime factorization, that's its prime factorization. We canceled out all the ones we could.
So you can take 2x, divide by the x, and just go 3 over x plus 4. Take an x out of 2x.
That's 2x, that's not an x squared.
Yeah, it's not x squared now, right? Yeah.
And even then, you can only cancel things out of a term if it factors out. You have to factor it out. I can't cancel an x out top and bottom unless I can get an x out both these terms and an x out both those terms. It's the only way to do canceling. You can only cancel out common factors. That's the only thing you can cancel. That's it. There's no, oh, cancel out 3 from the top and the bottom and leave me with x over 2x plus 1. No, nothing like that. You can only cancel out common factors. Because canceling out common factors is the same thing as multiplying by 1 or dividing by 1, however you want to think about it.
Okay.
Which doesn't change the number, right?
Yeah.
Okay. So now when we add fractions together, we need all the fractions to have the same denominator, right? And we call it getting the common denominator for a bunch of fractions.
Yes.
So when our fractions have a common denominator like this, they're relatively straightforward on how to add them. So we would write this as, if I were adding these 3 together, it's going to be equal to, we're going to have 5 minus 2x, we're going to have minus 1 minus 4x. So when you have a minus, it's always a good idea to write that term in parentheses so you remember to distribute the minus sign.
Okay.
Minus, in this case it's just a 6, but I will put parentheses if there's more than 6. All over whatever the denominator is, which is 3x squared plus 5. And then finally, you can add like terms. How many x's do we have? We have negative 2x plus 4x gives us a total of 2 x's. And then when we look at our constants, we have 5 minus 1 is 4, minus 6 is negative 2. Did I do that right?
Yep.
All over 3x squared plus 5. And so that's how we would have added those fractions together. Real easy when you have a common denominator. When you don't have a common denominator between all your fractions, it gets a lot messier. And you have to find what we call the least common multiple to get a common denominator. You need to find the least common multiple. So let's go over how you find the least common multiple. So let's look at a bunch of these numbers and find their least common multiple. A bunch of these polynomials. We have this thing, and this thing. And we need to find their least common multiple.
Okay.
You with me so far? Now,
Yeah.
Yeah. Okay. Now, as a general rule, we don't like it written in 3 minus x. We want the x on the left-hand side. So I want to swap those two terms so I can get a better feel for what this actually is. How can I swap those two terms?
You multiply it by negative.
Multiply by -1 flips the terms, right? if I have x minus 3, and I multiply that by negative 1, or sorry, 3 minus x, and I multiply it by negative 1, that's equal to negative 3 plus x, which is equal to x minus 3. And I can put the parentheses there. You with me?
Yeah.
So this term, a better way to write it out to get a better feel for what it has, is I'm going to rewrite it instead as negative 2 times x minus 3 times x plus 3. You good with that?
Well, what's wrong with what happened before?
It's just going to be easier for us to see when common terms show up if we pick a convention on how to always write them. For example, you might not have noticed that 3 minus x and x minus 3 are actually the same term. But if you adopt this convention, then that'll be more obvious to you. So here's one of our terms. Here's another one of our terms. We have 4 times x minus 3 times x minus 1. And then we have 3 times x minus 3 squared. Now our job is to find the least common multiple, which is the thing that has every single one of these as factors.
Well, that's obvious.
What is it?
X minus 3.
No, that's a factor of all of these. I need to come up with a term that has all of these as a factor.
What?
The least common multiple.
Oh, I know. I see what you're saying.
I don't.
Okay. The least common multiple between 12 and 16 is what?
2.
Now,
He's confusing least common
Okay,
greatest common
so
factor.
12 is the same thing as 2 squared times 3, right?
Yeah.
Yeah.
This is the same thing as 2 to the 4, right?
Okay.
So this has 4 2's and 0 3's. This has 2 2's and 1 3. So this one needs 2 2's, and this one needs 1 3, and then they'll be the same number,
Yes.
right? So 2 to the 4 times 3 is going to be what is their common multiple. Because notice that this is a factor of this, and this is a factor of this.
So you multiply all three of them?
And so this number, when you multiply it out, 16 times 3, what's that? 48. Notice 16 is a factor of 48, and 12 is a factor of 48. Or 48 is a multiple of 16, and 48 is a multiple of 12. It's a multiple of both those numbers, and it's the smallest thing that's a multiple of both those numbers. It's their least common multiple. It's a multiple of both those numbers, and it's the smallest one that's common to both those numbers. Least common multiple.
So you just have to multiply them all together.
Multiply them all together would give you a common factor, but we don't necessarily need to multiply them all together because then we get way more than we needed. Because notice before what we had, so we were talking about 12 and 16, right?
Yeah.
This was 2 squared times 3. This was 2 to the 4. If I multiply both those two together, I would get 2 to the 6 times 3. Now this is a multiple of both those things, but 2 to the 4 times 3 is the least common multiple of both those things.
Oh, I see.
So multiplying them all together does give you a common multiple, but it doesn't give you the least common multiple. So I need to add to this what these ones have that this one doesn't have. And I need to add to this what these ones have, but this one doesn't have. So what are the terms that all of them, or that at least one of them have?
X minus 3.
So notice that all of them, there's at least 1 3 showing up, right?
And all of them?
This has a 3, no, but there's at least 1 3 showing up. So our common multiple has to have a 3 in it, right?
Yes.
So it has to have a 3.
Similarly with the 4 and a negative 2 though, right?
Negative 2's and 2's count the exact same. So don't let the negative signs throw you off. So treat negative 2 and 2 as though it's the exact same. So this one has 2 2's, this one has 1 2. We can account for that with 2 2's.
Gotcha.
Okay? Now this one has 1x minus 3, this one has 1x minus 3, this one has 2x minus 3's. So we need 2x minus 3's. This one has 1x minus 1, those have none, so we need 1x minus 1, and we need 1x plus 3. And this is the least common multiple of these three numbers.
Where'd your negative 2 go?
Negative 2's come out the exact same as 2's.
So you'd have 2 squared for 4 and another 2.
Notice that this is a factor of this.
2 squared for 4 is a multiple of
And then, so you're just putting the 2 in that.
yeah.
Notice, look, if I were to factor this out of this, what would I be left with? What times, there's something times this that gives me this, and that happens to be negative 3 times 2 times x minus 3 times x minus 1. Notice that this times this gives me this, right?
Yeah.
So this is a multiple of that. So notice that the negative didn't really matter, that was a negative 2. Because then when you talk about what term do I have to multiply it by to get it, it just puts it in a negative there. It's the 2 that we really need to make sure we count for. The negative didn't matter
So
so much.
where's the 4 then?
2 squared.
And where's the 2?
Using the 2 squared.
So you have 3 2's.
Look.
2 2's.
You agree that this times this gives me this, right?
It does, but I don't understand why the 2 would disappear.
Hold on.
I guess it just does.
Oh, no. Make sure you... So you're saying you don't see how this times this gives me this?
I don't see how that 2 is in the bottom one.
This 2?
Yeah, how is that 2 shown in the bottom?
Okay, so negative times negative gives me positive 1. So my negatives are gone. 2 times 3 times 2 is the same thing as 3 times 2 times 2. We have 2 2's. It's 2 squared.
4 is 2 squared though, on its own.
I'm saying that this term times this term gives me this term.
Okay. I believe it does.
You believe it does?
Yes.
So then, if this times this gives me this, then this is a factor of this. Because I can multiply it by something to get this. The same way, how do I know that 3 is a factor of 12? Because there's something, namely 4, such that 3 times 4 gives me 12. I know that 5 isn't a factor of 12, because you can't find something that I multiply 5 by to get to 12. So since I can take this and multiply it by something to get this is a factor of this. Make sense?
Not really. I want to say yes to get it done with, but no, it doesn't.
It doesn't make sense that the one in this box is a factor of this.
It doesn't make sense.
All it means to be a factor is that I can multiply it by some other polynomial to get this polynomial. If I can do that, it's a factor by definition.
And you got that number you're multiplying by taking every number in every other of the 3 equations that the one doesn't have.
I just looked at this and I said, what does this need to have to become this? And I wrote those things right there.
And it needs 2 squared.
No, it just needs a 2.
Because the 4 is a 2.
4 is the same, look, this 4 can be rewritten as 2 squared.
Yeah.
But I don't even know why you're looking at this term. Ignore this term.
You need all 3.
Ignore these 2. These 2 out of the picture. Ignore them.
Okay.
This term times this gives me this. Correct?
Yeah.
So then this is a factor of this. Okay, so you're good with that. Stop. Now we look at this one. For this term, what do I need to multiply it by to get this? I need to multiply it by a 3, and I need to multiply it by it needs another x minus 3, and it needs an x plus 3.
And it needs a negative 2.
No. In order for me to turn this into this, I need to multiply by this.
Okay, so why doesn't the bottom one have a negative 2? Or a 2?
Look, if I say what are the factors of 12, I can say 3 and 4, and I can say 12 is also negative 3, negative 4. When we had a negative here, we just had a negative in the next term that we multiplied it by to get positive again.
His question is, why isn't there an extra 2 in your big least common multiple?
There's only 2 2's in that one, and there's 3 2's in the 3 above there.
There's 3 2's.
There's the 4 and the negative 2, and then below there's only the 2.
So you're saying there's a 2 here and there's 2 2's here, so there should be 3 2's here.
Yeah, why is there not?
Okay, let's go back to 12 and 16. 12 was equal to 2 squared times 3. 16 was equal to 2 cubed. Or 2 to the 4, sorry. Their least common multiple, 48, was 2 to the 4 times 3. Notice it doesn't have 6 2's. It only has 4 2's.
Because the 2 2's are already in 4's.
Yeah.
2 4's.
Right. This has 1 2. This has 2 2's. This has 0 2's. The most 2's that show up is 2 2's.
Yeah, I can see that. That's the least common.
Okay. Whatever makes it quick.
So you said negatives don't matter, right?
Negatives don't really matter because you just make the other term that you multiply by a negative and it comes back to positive.
But what about your
Like
x
if I
minus
know
3?
that 12, look, when we're looking at 12, if you tell me any number is a factor of 12, 4, I get, okay, and negative 4 is also a factor of 12. For free. I didn't even have to think about it.
Yeah.
Because notice when you find factors, when you find a factor, you find two numbers. You say 3 and 4 multiplied together give me 12. I say, oh yeah, I'm also negative 3, negative 4. You say, no joke. The negatives don't change anything. You did all the work finding the numbers. And if I just piggyback on yours and put negative signs on there, it still gives me it.
Yeah.
It's just the same numbers.
I understand that.
Yeah,
But
that's all the negatives do.
why are you leaving it at x minus 3 and x minus 1 then?
Because the negative in there doesn't matter. The factors of 12 and negative 12 are the same.
So you're just doing it for convenience because it's
It just makes it right prettier.
okay.
Yeah. So the negative signs don't change anything when you're finding factors.
So why don't you just write it all in positives?
I did.
No, you had an x minus 3.
Well, is that positive or negative? That depends on your x.
Oh.
You can't really call that a positive term or a negative term.
Okay.
I wrote it in whatever order I wanted. Because it didn't matter which order I wrote it in.
Gotcha. That makes sense.
Yeah, because you can't really call it positive or negative because x is a variable. So is the whole thing positive or negative? Bad question. Okay. Anyways, don't think we're going to get to complex numbers today. But that's fine. It's better to flesh out all the small details early on so that they don't confuse you later. Alright, so now we're going to add two fractions together. So in adding two fractions together, the first thing we need to do is get a common denominator. And the common denominator that we want is the least common multiple of the denominators. So I am going to add these two fractions together.
Okay.
And so first thing I want to do is find the least common multiple of those two denominators. So one of the numbers I'm looking at is 9c minus 6d, and the other one I'm looking at is 4d minus 6c. Right?
Yeah.
Now, first thing I'm going to do is I'm going to rewrite this as negative 6c plus 4d, just to put it in the same order. You with me?
Yeah.
Okay.
So, our common multiple then is, and we can factor a negative out of this one if we want this term to be positive and that term negative. That's not going to change anything. So we can factor a negative 1 out of that and make it negative, like that. Won't change anything. Okay, so now we need our common multiple of both of these. This one up here can be rewritten as, we can factor a 3 out of that one, right?
Yes.
So if we factor a 3 out of that one, that's going to be 3c minus 2d. And if we factor a 2 out of this one, then that's going to be 2 times 3c minus 2d. Right?
Okay.
And so our common multiple is going to be what?
3 times 2. Oh, times 3c minus 2.
Okay, so there is a common multiple of both those things.
The least common multiple.
The least common multiple. Sure. So this is what we would use as our denominator when we add these two things together. I'm going to multiply this one top and bottom by whatever I need to make it come out to that. And I'm going to multiply this one top and bottom by whatever I need to make it come out to that.
Okay.
So the denominator I'm after is 6 times 3c minus 2d. That's the common denominator I'm after. So I'm going to write this as 5 over 9c minus 6d times, what do I need to multiply this by to get that? 2. Right? 9c minus 6d is this.
Yeah.
I need to multiply it by 2 to get to this.
Yeah.
Okay? So we need to multiply this one top and bottom by 2.
Okay.
Plus, for this one, we have 7 over 4d minus 6c. What do I need to multiply this one top and bottom by to get this?
Well, that one's just 3.
Almost. Negative 3. Negative to flip it, 3 to get it.
Gotcha.
So multiply this one top and bottom by minus 3. You with me?
Mm-hmm.
And when we do that, 5 times 2 is
10.
plus 7 minus, well, what's 7 minus 3? Negative 21. 10 minus 21 is? So we get negative 11 over our common denominator.
Okay.
Make sense?
Yeah.
Alright. Another one. Put these two terms together. So, first thing we need to do is find a common multiple between the denominators. So one of our denominators is x squared minus 9. And another one of our denominators is x squared plus x minus x.
Didn't we just do this?
I don't know.
Okay.
First thing we want to do is factor these things. So x squared minus 9 is?
X plus 3 times x minus 3.
Right, that's a difference of squares. Okay, this one is equal to, we need x and x, multiply together, give us negative 6, add together, give us 1. What's it going to be?
3, 2.
Positive 3 and negative 2, right?
Yeah.
Positive 3, negative 2. Okay, so what's the least common multiple of these two terms then?
Well, they each have an x plus 3
They each have an x plus 3.
times x minus 3 times x minus 2.
So here's our least common multiple.
So true.
Okay, so now let's do our addition. So we're going to do this term. So it's 4x over x squared minus 9. And what do we need to multiply it by top and bottom to get our common denominator?
Just x minus 2.
This one needed the x minus 2, right? So we multiply top and bottom by x minus 2. We're multiplying the whole thing by 1, so it doesn't change our number.
Yeah.
And then we have minus. I'm going to do plus, and I'm just going to put the minus up here with this. So minus, we have negative 3x. So I put the minus with the 3x. Over x squared plus x minus 6. And what do I need to multiply this one top and bottom by?
X minus 3.
X minus 3. So it had x plus 3 and x minus 2. It needs the x minus 3. So I'm going to multiply this one top and bottom by x minus 3, x minus 3. Everyone follow that?
Mm-hmm.
Yep.
So now I don't need to do any algebra with the denominator. I know what my denominator comes out to. It comes out to this. So all I care about now is the numerator. So in my numerator, multiplying this by this, maybe put parentheses here to remind us that we need to distribute. 4x distributed into that, we're going to get 4x squared minus 8x, right?
Yes.
And then for here, we're going to have negative 3x squared plus 9x, right?
Mm-hmm.
All over our denominator d. We'll just call it thing d for denominator, so we don't have to rewrite it. Which is equal to, add like terms,
X squared plus x.
x squared plus x. Right?
Mm-hmm.
I just really like that to see if something else was going to cancel with our denominator. Nothing else was. So we could have left this x squared plus x. If we wanted. And our denominator would have been, I think.
Yeah.
Good? Okay. Maybe we'll just do this example. guys are pretty much getting it. So this example, we're doing this fraction divided by this fraction, right?
So the top times the reciprocal.
Or this fraction multiplied the reciprocal of this fraction, right?
Yeah.
So this is going to be some hairy algebra. Maybe we'll get rid of that line to get plenty of space. So we're going to have 2x squared plus 7x minus 15 over 2x squared minus 3x minus 14. And we're going to multiply by the reciprocal of this. So we get 2x squared minus 19x plus 42 all over ax minus 12. Right? Now we factor everything to see what cancels out before we go crazy doing this super ugly multiplication. So let's rewrite this term. We're going to have a 2x and an x. And it's going to be a plus 5 and a minus 3. Oh, that's super crooked. Right? 5 times 2x is 10x minus 3x gives us 7x. In the denominator, we're going to have 2x and an x. What's that one going to be?
Just a 7 in the 2, I guess.
Minus 7 here, plus 2 here, right? So we have negative 7x plus 4x gives me minus 3x.
Gotcha.
Times, factoring this thing out, we're going to have 2x and an x. Let's see, 42. 42, we could write that as 7 times 6.
So that's not what you
Or
want.
negative 7 times negative 6. Or negative, oh, maybe that is right.
Yeah,
Negative
7.
6, negative 7.
Yeah.
Yeah, I just put them in the right spot. Negative 6, negative 7. So multiply those two together, you get 42. 2 times negative 6 is negative 12x, minus 7x is minus 19x. And now in our denominator here, factor out 4. So we get 4x minus 3, right?
Yeah.
Okay, so let's see. 2x minus 7 cancels out with 2x minus 7. Is that all that cancels?
Should the x minus 3 cancel out with the x minus 3?
Where's x minus 3?
2x minus 3 and x minus 3.
No.
Oh.
Let me look at his and see if he only cancels those. Oh. No wonder. When you pull out a 4, you still have a 2. No, you were wrong. X minus 3 definitely doesn't cancel out with 2x minus 3. 2x minus 3 cancels out with 2x minus 3. Okay, so now those all cancel out, and that's better. So in the numerator now, we get x plus 5 all over, or x plus 5 times x minus 6 all over 4 times x plus 2, which is our answer. And you can multiply that out if you want, but now that's real easy to multiply out.
Okay.
Right? How's our camera doing? Is it saying low power mode yet?
Nope.
No? Okay, so maybe then I can briefly introduce complex numbers and then we'll reintroduce it next time as the reminder. So complex numbers. So going back to our pesky negative numbers, taking the square root of negative numbers. You might remember last time we proved that there is no real square root to a negative number. For example, negative 4. plus the square root of negative 4. There is no real number such that when you square it, it gives you negative 4.
Yeah.
Every real number is either positive, negative, or 0. A positive times a positive is positive, a negative times a negative is positive, and 0 times 0 is 0. So I can't multiply a real number by itself and get a negative number. That doesn't happen. You with me?
Yes.
So, when we talk about the square root of negative 1, there is no real number that gives us the square root of negative 1. Doesn't exist. No real number does it. So, we're going to come up with our own number, and we're going to call I. And we're just going to say, let I equal the square root of negative 1. And we know that I is not a real number. Right?
Okay.
The same way that pi is not an integer, I is not a real number. It's a different kind of number. Not a real number. Make sense?
Yeah.
Okay, so by definition, what's I? We're going to call it the square root of negative 1. I is not a real number. It is not in the set of real numbers. It's not in there. We know that. And it's by definition, negative 1. Okay, or the square root of negative 1. Good so far?
Yes.
Question, what's I squared?
Negative 1.
Negative 1. If I is equal to the square root of negative 1, what's the square root of negative 1 squared?
Negative 1.
Negative 1. Right? So I squared is negative 1. What's I cubed?
Negative I.
Negative I? 1? Well, think about it. I cubed is the same thing as I squared times I. I squared is negative 1, so we get negative 1i. Or negative I. Make sense?
What? Oh, okay.
Alright, what's I to the 4?
Is it just
1.
Well, we can rewrite that as I squared times I squared, which is negative 1 times negative 1, which is 1. Good? And so maybe just write out this pattern really quick because it's a good pattern for you to know. I to the 1 is equal to I. Maybe we can write I to the 0 really quick. What's I to the 0 equal to?
1.
1. Anything to 0 is 1. Okay?
Okay.
I to the 1, I. I squared, negative 1. I cubed, negative I. I to the 4, 1. I to the 5, I. I to the 6, negative 1. I to the 7, I. And it goes between these. It goes 1, I, negative 1, negative I. 1, I, negative 1, negative I. And it filters like that. So when I see something like I to the 100, I instantly know that's equal to 1. Because 100 is a multiple of 4.
Yeah.
Because this is the same thing as I to the 4 to the 25.
It's also multiple of 2.
2 is a negative.
Alright?
Yes.
Let's try another one. What's I to the 1003?
I.
No.
Negative.
Negative
Negative
I.
I.
Negative I. You knew it was odd, so it had to be I or negative I. Because all the evens come out real. Ones are negative ones. Negative I. I to the 1000 is 1. So I to the 1001 is I. So I to the 1002 is negative 1. So I to the 1003 is negative I.
Yeah.
Make sense? Quick tricks for quickly calculating I to high values. Okay. So, now get to our definition of a complex number. So let A and B be any real numbers. A could be pi, B could be 2. A could be 17, B could be negative 2,467. They're just any two real numbers. Let A and B be any two real numbers. Then A plus B times I is called a complex number. What's a complex number? It's two real numbers where one of them is multiplied by I.
Does it have to be
We call
two
that
real
the-
numbers?
Yes,
Can it just be like B times I?
that's the same thing. You just chose 0 for your A.
Oh.
That's 0 plus B times I, where B is some other real number. So yes, always in favor, pick any two real numbers you want, plug them in right there. It's a complex number.
How about 3 numbers?
Where would you plug them in?
1 plus 2x plus xi.
There's only an A and a B there. Where do I put my third number?
Well, I'm saying what if you had 3 numbers and one of them had an I in it? Would it still be a complex
Pick any
number?
2 real numbers. I is not a real number. Can't pick I. Pick any 2 real numbers, members of that set.
Okay.
Then your first real number plus your second real number times I is called a complex number. And the set of all possible complex numbers we represent with C with a line on the left-hand side. With me? There's going to be a proper chapter way down the road where we reintroduce complex numbers. This is like the intro, basic review of complex numbers. So we'll get back at these again, so don't be too intimidated.
Okay.
Anyways, so now notice that for any real number A, I can rewrite A, for any real number A, I can write A is equal to A plus 0 times I, right?
Yes.
Did I change A when I rewrote it as A plus 0 times I?
No.
Did that change A in any way? So it's still the exact same number, right? Notice that A plus 0 times I is now a complex number. So I just really showed that any real number is a complex number. Not any complex number is a real number, but any real number is a complex number. So the real numbers are a subset of the complex numbers. The same way that the integers are a subset of the rationals. I can represent any integer as a fraction, just divided by 1. Now it's a fraction. I can represent any real number as a complex number, just add 0 I. Now it's a complex number.
Yeah.
Make sense? Very similar thinking. So that's the complex numbers. And we'll go over addition and multiplication on them later next week. Just wanted to give you a basic introduction to the complex numbers. That way you can introduce them to you twice and hopefully you get comfortable with them. So we'll call it there. Shoot, we didn't go over any exercises. Oh well. Looks like people after credit aren't here anyways.